Welcome back to the lab. I'm excited to be here. I hope you are too. Welcome back to EE for Everyone. Today we are continuing our comparator series. We're going to teach you a little something about circuit analysis. And today we are talking about Kirchhoff's current law and nodal analysis. This is one of my personal favorite topics, maybe because I wrestled with it so much in university, maybe just because I think it's fun. So in a previous video, we were just talking about Kirchhoff's voltage law, or KVL. Check that out. Wait. Oh, nice. Yeah. Check that out. If you haven't, gestured in the right direction. Love it. Anyways, so this is a little different. This is a little different than that. Today, we are talking about Kirchhoff's current law. It's same, only different, where this is another modification of Ohm's law to apply it to a different situation. So what are we talking about? Before we were talking about meshes, right? We're saying we've got current loops. We've got loops of current, and we are going to see how that's flowing through components to think about Ohm's law in a different way that makes it more easy to dive into complex circuit networks. Great. What are we doing today? Well, today we're talking about nodes. What is a circuit node? Let's say we've got something like this. We've got V1, and we've got a resistor. We got a resistor. We got, that one's a silly resistor. We've got a resistor. Even more. Okay. Yes. Great. Great. And just for good measure, let's add another voltage source over here with, you guessed it, a resistor. Okay. Oh, four-way net connection. No. Okay. Okay. So now we've got an R1, we've got an R2, we've got an R3. And we've got an R4 with, for good measure, an R5. Okay. So I want to focus in on one piece of this puzzle, and that is right there. I want to focus in on that node. What is that node? Well, this node is a fixed voltage point, right? What do we have? Electrically, we have 4 resistors tied together with what we're going to assume are ideal traces. And we don't really know whether current's flowing in or out. We know there is some current. So yeah, but we know that if there's some current flowing into, let's say, a couple of these nodes, and some current flowing out of a couple of these nodes, what Kirchhoff's current law tells us is that the sum of all of those currents must be equal to 0. Why do we know that? We know that because if there were a current imbalance, if there was more current flowing in than going out, more current going out than going in, that would mean that the voltage is changing. There would be a rate of change in the voltage. There would be a charge imbalance. And physics does not like that. No. That's occasionally possible if you've got like a charging capacitor situation. Occasionally. But that's only in transient conditions, not steady state. This is a steady state analysis, so that is simply not possible. You can't have a rate of change on your voltage in steady state. Okay. So that is why our net current is 0. So if we were to write that out analytically, we would see, okay, we need to label our nodes. We've got node 1, node 2. Today we're working with a modified version of Ohm's law, and that is current. So we are looking at the currents, right? The sum of currents. And so you know that current is equal to V over R. If that's not familiar, definitely check out our last video on Ohm's law. Definitely. Okay, so with that in mind, now we're going to start to build our equations. And the most critical step is making sure that we set up all of our currents in the same way, because that means that our signs will all balance out. So if we're building the equation for node 1, we would say that 0 equals the voltage at node 1 minus V2 divided by R5 plus the voltage at node 1 minus voltage at node 2 divided by R3 plus the voltage at node 1 divided by R2 plus voltage at node 1 minus V1 divided by R1. So now that's all the currents flowing into node 1 are set equal, right? We're saying that if we add every single current, regardless of the directions, regardless of which ones are positive and which ones are negative, regardless of all that, we know without a doubt that that'll work out. We know that the sum of all of those currents must be 0. Okay. What else can we do? Well, there's another node here. Okay, so if we build the equation, so this was N1, we're going to build it for N2. So that's pretty easy one. We're basically doing the same thing, right? We've already got a current direction decided for R3. So we're going to basically build this next equation the same way so that all the currents are flowing in or out appropriately so we can sum them. 0 equals, and then when it was the head of the arrow, we were putting that first. Excellent. Okay, so we're going to say that's VN1 minus VN2 divided by R3 plus VN2 divided by R4. That's the whole equation. And actually, those are only 2 nodes because this is fixed at V2. This is fixed at V1. Those are known voltages. Heck yeah. So that's actually the whole, there's only 2 nodes, right? There's this junction. I think the node is formally defined as a connection of 2 or more components. I suppose we could have just done a series combination to simplify that and remove node 2. That would be an option. I should have added a resistor there to make that impossible. Dang. Anyways, so in this case, because we've got one more complicated situation and one more simple situation, I think our path forward is clear. Let's find a way to eliminate one of these variables. Not really sure how I want to leverage this, so let's just finish out this example by plugging in some numbers. Let's say, for example, that we wanted to solve for the voltage across R4. We wanted to solve for the voltage across R4. That would end up being equal to node 2, the voltage at node 2. Okay. And if we want to know that, unsurprisingly, this equation tells us that that's a function of the voltage at node 1 and the ratio of R3 and R4, which that checks out. And our first equation would, let's see, what do we have to do to find node 1? Oh, that looks like partial fraction decomposition. All right, so I super definitely plug this into Wolfram. And you can see what I do here. Basically, I assign a single letter variable to all of these things. So I tend to in this case where we got a bunch of voltages and a bunch of resistors, I give all my voltages A, B, C, D, E, and then I start Z, W, X, Z, Y, X, W. Yep, I think that was right. Backwards is hard through the alphabet. Anyways, so I do one way, one the other way, and then I plug it all in. And man, that punched back. Basically, I solved for what is the voltage at node 1, and it spat out an incredibly long polynomial function, which I'm sure is correct, right? It's partial fraction decomp. There's a lot of terms here, right? There's a lot of things that don't break down because you basically need to find a common denominator and combine it all. And the common denominator is not very simple. So yeah, these are the nicknames. Yeah, this was one of my least favorite parts of doing this analysis. I love the theory of it. I love the application of it, but just crunching the polynomial math, there's a better way. And that way is something like MATLAB or MathCAD or Wolfram Alpha, like computational tools built into computers that are great at exercising rules. So at any rate, that's my perspective. Maybe you got a different perspective, and that is okay. But no matter how you want to solve this, basically what that does, right? That gives us an incredibly complex polynomial where if we were to plug in values, right? So let's say this was the general form of a circuit, just like with KVL, we could run through, plug in some numbers, and calculate the rest, however that made sense. But I don't want to leave that quite there. I want to do the same thing that we did before. We're going to start this with a simple example. And that is, right, this is Kirchhoff's current law. So just like a voltage source plugged very nicely into the equation before, we need to plug a current source in if we want this to really work out. This is R1. This is I1. Okay. And applying KCL, Kirchhoff's current law, we end up with I1 minus, we're going to call this node 1, V node 1 times R1 divided by R1 equals 0. There we go. So this is the voltage applied across the resistor divided by the resistance, which is a current. It's effectively a current. All right, let's see if this balances out. So let's think about this from Ohm's law perspective. Right, we've got voltage, resistance, current. I'm not sure how to bring this home. For KVL, it felt obvious because we were able to build these equations in the same way. Oh, they don't have the same form. Yes, let's move this down here. So voltage divided by resistance equals current, because we know V equals I times R. So what we did is we divided both sides by resistance. That's the form that we get. Great. So trying to make this look the same. What is the voltage across our resistor? Well, that's VN01. Okay. Our resistance is R1. Our current is I1. Okay. So how do we resolve this discrepancy? We've got this negative sign. We've got a 0. It doesn't look quite exactly the same. Well, let's try adding that resistance to both sides of the equation. There we go. It's that easy. So you can see that simply by moving this over to the other side of the equation, we're able to very quickly verify that building the KCL equation, where it's the sum of all the currents in and out of a node are equal to 0, is in fact the same. Right? I didn't really do anything different here, right? This is the voltage across that resistor divided by the resistance. This is the same thing, except we subtracted 0, right? That's the difference. There's a -0 because the voltage on the other side of that resistor is 0, because this is our ground reference. Hopefully I didn't get too lost. It was definitely a challenge to switch gears from Kirchhoff's current law switch gears from the voltage law to the current law back to back. I'm sure you noticed we haven't moved. The sun hasn't moved. We did these back to back. It's a little tricky to do them one right after the other. Got to kind of flip your mind from voltage to current. They're both good. Apply them when they make sense, right? Like we just demonstrated, Kirchhoff's current law is fundamentally, it plays nicer with current sources. If you've got current sources, maybe use KCL. If you like nodal analysis better than mesh analysis, use it. I think you can tend to use either method for any circuit. It's just for some circuits, one approach might be more work than the other. There's no wrong answer because ultimately these are all based off of Ohm's law. If you want to take the time to basically combine all the parallel elements and expand them back out and do simple Ohm's law for everything, you can, but there comes a point where the circuit gets complex enough and you just need to break out the more advanced tool. As a supplement to this, just in case it wasn't super easy to follow, I think what I'm going to do is put some resources down in the description. I think that will be very helpful. Just some notes from maybe a college that posted some lecture slides online or something. But if you got more questions, if this didn't make sense, if this format isn't working for you, let me know what I can do to make it work a little better, and we will take it from there. If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we're going to apply Kirchhoff's laws to dive into a complex circuit network. It's going to be awesome. If you'd like to support the channel, don't forget to hit that like button, get subscribed, or consider checking out our Patreon page linked in the description. That really helps us out a lot. Thank you to everyone who's decided to support us. You are a big part of keeping this all possible. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thank you for watching EE for Everyone, and thank you for staying till the end. Bye.